All right, I want to look at a couple homework problems in chapter 8, and I want to show how similar they are to some of the problems we did in chapter 2 where the car goes down a road. Okay, so this first one here, okay, so pitcher throws a curveball. Okay, so read through this. So I drew a picture. Here's the person throwing the ball. Here's how far it's going to go. All right. Okay, so if you read through this, this is the exact same as this picture from chapter 2. Okay, so for example, back in chapter 2, we would say the car has some average velocity. They give us the average velocity. They tell us how long, they give us the time it takes to drive that distance with that average velocity, and then they ask how far it's gone. Okay, well, that's the definition of average velocity, and then you're just asked to find the displacement. Here, you're doing the rotational equivalent of that. Okay, so something is spinning with some average angular velocity omega. Okay, omega average that they give us. They tell us the time that that's happening, and they want to know, okay, how many times has the ball rotated on its axis? Okay, not exactly how many revolutions does it do, but they want to know how many radians. Okay, so if the ball was thrown slow enough that it only rotated once, by the time it got there, okay, it would go around one revolution, then the angular displacement would be 2 pi radians. Okay, so this thing is rotating fast. Okay, so they asked for what's the angular displacement. So just like this problem in chapter 2, average angular velocity is angular displacement divided by the time. Okay, here they give us the average angular velocity, they give us the time, and then I can just solve that for the angular displacement. That's what I did right here. Okay, but they give us the average angular velocity, but not in the correct units. They give it to us in radians per minute. So remember, omega, the angular speed, has to have units of radians per second. Okay, so right here, okay, I converted that to radians per second. So I said in 1 revolution, I have 2 pi radians, and then in 1 minute, 1 minute, I have 60 seconds. So this gives me omega in the correct units. Okay, so then my angular displacement, okay, using this, my angular displacement is the average angular velocity times the time. So there's my average angular velocity, okay, in radians per second, times the time, and the seconds cancel out. Okay, so look over question 2. All right, so you have a Ferris wheel rotating around. They give it the angular speed. They say it starts from rest, okay, and they give you the angular acceleration. They want to know how long does it take for that to come up to that speed. Well, that's the same as in chapter 2. You have a car at the light, which we did a couple months ago. Car's at rest. The car accelerates. Okay, they give you the final velocity, and they want to know how long did that take. Well, that reminds you of equation number 1. Okay, so it's the same thing here. Okay, except now it's going in a circle. All right, so they give you the final angular velocity. You have the initial angular velocity. They give you the angular acceleration. Find the time. So I wrote equation number 1, okay, written in terms of the angular quantities. Okay, so they give you omega initial is 0. They give you omega final in the correct units, radians per second. They give you alpha in the correct units, and then just solve that for the time. Okay, so look at question 5. All right, so here they have a drill, and they give you 2 chunks of information. Okay, they tell you that if the drill is already moving with that spin rate, okay, with that angular speed, okay, that the drill can speed it up to that angular speed, all right? And when it does that, when it goes from slow to fast, it goes through that angular displacement. Okay, so let's say it's spinning at 2 revolutions per minute, now it goes to 10 revolutions per minute, and it happened over maybe 30 revolutions. Okay, that's what it's saying. It goes from a slow speed to a fast speed, and it rotated around so many times, okay, which means so many radians, all right? And it says, assuming a constant angular acceleration, which means we can use our kinematic equations, they want to know, okay, well, how long now would it take to reach that omega final, okay, starting from rest? Okay, so for the first chunk, so from here to here, this is the information they give you. They give you omega initial, omega final. That's how many times it rotated, okay, in radians. All right. Now they say, okay, what's the time it takes now to go from rest to that final speed? Well, you have to find the angular acceleration alpha. And looking at these, the pattern is, you know, omega initial, omega final, and the angular displacement. So equation number 3, right, has the initial angular speed, final angular speed or angular velocity, and the angular acceleration, okay, you can find because they give you your angular displacement. So everything in here is known except for alpha. Okay, so put in these numbers, you get alpha in radians per second, okay? Okay, now it says, okay, now that you have the angular acceleration of the drill, okay, so the manufacturer makes the drill have a certain angular acceleration. Now it says, okay, you start from rest, they give you the final angular speed, that's still the same number, angular acceleration is still the same number, okay? What's the time that it takes now to come up to that faster speed using the same angular acceleration for the drill, all right? So that's equation number 1, okay? It starts from rest, they give you omega final, there's your omega final, okay? Alpha you found there, and they ask you to find the time. Okay, so this one's a weed whacker, all right? So here's my picture of the weed whacker. So here's the little cable, okay, that's rotating around, all right? And they tell you the string rotates at an angular speed. Okay, now that's omega, but it's not the correct units, right? Because omega has to have units of radians per second, okay? So remember, you can always change radians per second by saying in 2 pi radians, you have 1 revolution. Okay, so that number 48 is omega, but not in the correct units. And they give you the tangential speed. So that 53 is V. Okay, so they want to know the length of the string. Okay, well, look in chapter 8. We know that for something that rotates, okay, so this thing has some linear speed V, and V is R omega. So they're asking you to find the length of the string, which is the radius of the circle, which is V over omega. So they give you the speed, they give you omega, but you had to convert it into the correct units, right? You can't leave it with the word revolution. Okay, you have to say 1 revolution is 2 pi radians. Okay, and that gives you the radius of the circle, or the length of the string. Okay, so this one is actually a good review from the old stuff because I drew the picture. You have a ball, they give you the radius, okay, has a constant linear speed. Right? Now, what they mean by that, and we went over this, okay, is that different parts of the rolling ball have different speeds. Remember, V is R omega. But when they say it rolls with a constant linear speed, they mean, okay, that's the speed of the center of mass, okay? So if this was a car, okay, you're in the car, that means the person would be moving at that speed. Okay, that means the door handle would be moving at that speed. Okay, the entire car is moving at that speed. Okay, which is what the axle here, okay, the axle there is doing. Okay, so that's the speed of the center of mass. It rolls off the table. They give you the distance that it falls, and they want the angular displacement of the ball while it's in the air. So what this means is this ball is rolling. Okay, so the ball is rolling. Get rid of that. Ball's rotating. Okay, when it leaves the table, okay, the ball is still rotating, and there's nothing that can change that rotation rate. So they want to know how many times does the ball rotate? How many times does it go around? Okay, not exactly how many times does it go around. That'd be revolutions. They want it in radians. Okay, so angular displacement essentially means how many times does it go around in a circle, but they want it in units of radians. Okay, so the thing is, you need to find the time it takes to fall, and that's going back to our earlier projectile motion chapter. So I have my coordinate system, okay, and this is just like we did in lab, all right? So that's the ground is my origin, that's my 0, 0, okay? And again, the pattern is you have no idea what the speed of the center of mass is when it hits the ground, okay? So don't use an equation that has a V final. So this gives us equation number 2. To write down equation 2, I put in the correct sign for A, so AY is G. V0y is 0 because it's coming off horizontally. So I can solve this for the time. Okay, and in my coordinate system, my delta y is positive 2.4. Okay, so this gives me the time it takes to fall. All right. And then, okay, I put a reminder here that while this thing is in the air, there isn't anything that can change the spin rate. Okay, so whatever omega it has here, omega initial, is the same spin rate when it hits the ground, omega final. So the omega, okay, the omega doesn't change. That's 0. Okay, so that means that there's no angular acceleration while it's in the air. Okay, the ball spin rate doesn't change. Okay, spin rate can't change. Okay, so it'd be different if the ball was rolling down a steep hill. Okay, you let go here, it's not spinning. As the ball goes down the hill, it goes faster and faster. Okay, here it's in the air. Okay, nothing can change the spin rate. So I'm trying to find how many times does the ball rotate. That's my angular displacement. So that's why I picked number 2, because we have no idea what we have no idea how fast it's going at the bottom. Okay, and they give us omega initial because we know the spin rate when it leaves, and we know the time it takes to hit the ground, and alpha is 0. All right, and let's see. Yeah, and if I wrote the other one, right, omega final is equal to omega initial plus alpha t. Okay, these are equal. Okay, those are equal, and alpha is 0. So that just says omega initial equals omega final. And equation number 3 would tell us omega initial equals omega final. So only equation 2 gives us something to work with. Okay, so that's 0. Okay, now I'm trying to find my angular displacement. What's the initial angular speed when it leaves the table? Okay, so this thing is rotating when it leaves the table. And we know when it's rolling, V is r omega. So I solve this for omega. They give us the speed of the center of mass. That's my 209. They give me the radius of the ball. Okay, and when I do this, the m's cancel out, and I have units of 1 over seconds, right? So I have 1 over seconds. And then, because we know omega has to have units of radians, and then you get to write the word radian right there. Remember, radian is a dimensionless quantity, okay? It wouldn't be appropriate to leave it off, so you want to write the word radian. So omega has to have the units of radians per second. Okay, so here's my angular displacement. I now know my omega spin rate when it leaves the table. That's my 10.45. They give me I calculated the time, and that's my angular displacement. Okay. Now, if you look at the answer I have posted up there, okay, I found that answer is different because when the book did it, they used G as 9.81. So that's why I got 7.313 and they got 7.309. Okay, so that won't affect your answer.